So at this point, we've developed several tools that we can use to find the roots of polynomials or to factor polynomials. What we're going to do in this lecture is we're going to kind of bring all these together and see how we can use them to completely factor polynomials or solve polynomial equations. So let's start by thinking about how we can factor this guy here. Right, so I like to apply Descartes' rule of signs first. It's usually, I think, pretty straightforward, at least for finding the positive roots. So if we do that, you'll see we've got 1, 2, 3 sign changes here. Right, so that tells me I have to have either 3 positive roots or 1 positive root. Right, so what else does that tell me? What do I know about the negative and the complex ones? Well, because this is a third-degree polynomial, it has at most 3 roots or 3 factors, which means if it has 3 positive ones, then the other 2 are both going to be 0. Now, if it has 1 positive root, I have 2 possibilities. One possibility is there are 2 negative and 0 complex, or the other option is I have 2 complex and no negative. Now remember, I couldn't put 1 over there on the complex side. I couldn't have done 1, 1, and 1 because the complex roots from the complex conjugate root theorem, they always come in pairs. So that number in the complex column always has to be even. All right, so let's do the negative version of Descartes' rule of signs and see if that helps me maybe eliminate one of these 2 options. All right, so let's see. What do I have to do? I'm going to evaluate the polynomial at negative x. So I'm going to put negative x in here for all of these x's. This becomes negative 6x cubed minus 13x squared minus 9x minus 2. And you see that did help. There are no sign changes there. Right, because there are no sign changes, that tells me that there are no negative roots, which means this last column here, this last row, has to be the one that works for the 1 positive root. So this one here, this 1, 2, 0, 1, this is not a possibility. Right, so I'm going to have either 3 positive roots or 1 positive and 2 complex ones. All right, so now I'm going to clean up a little. I'm going to make a little space. I'm going to start thinking about the rational root theorem. And what does that tell me? Well, the factors of the constant term are 1 and 2, and the factors of the leading coefficient are 1, 2, and 3. All right, now notice I didn't put the negatives on here for this one, right? I'm going to save myself the effort because I know there are no negative roots, so there's no point in even considering the negative values. All right, so let's see. Now we're going to take the ratios here. 1 divided by 1 is 1. Right, and I always stop and think, make sure I'm getting these in the right order. 2 divided by 2 is 2. 1 divided by 2 is a half. Here we get 1/3. 2 divided by 2 is 1, but that's a duplicate. And then we have 2 divided by 3. So these are our only possibilities. All right, so now I'm going to apply the remainder theorem, and it's going to be just a very brute force kind of situation. I'm taking all, what did I end up with? 5 of these numbers and plugging them in there and seeing what happens. And you can do these by hand. You can go to Excel if you like. If you're doing them by hand, start with the easy ones, right? First, let me, I'm going to cross this one off just because that one's a duplicate. The others are all unique. All right, so if I take this thing and I'm going to call this P of x. So if I evaluate P of 1, that's 6 times 1 cubed minus 13 times 1 squared plus 9 times 1 minus 2. That's 6 minus 13. That's minus 7. Plus 9 is plus 2. Minus 2 is 0. There you go. Awesome. So P of 1 is 0. Therefore, x minus 1 is a factor. Right now, you've got two options how you can proceed from here. One is you could divide x minus 1 into that polynomial. If you do that, you're going to get a quadratic polynomial out. And quadratic polynomials are pretty easy to factor. You can always fall back on the quadratic formula if you like. Or you can continue evaluating these guys over here and see which ones come out to 0. And if you do that, you should see P of 1/2 equals 0, and you should see P of 2/3 equals 0. So what does this tell me in terms of factors? We really don't want to say x equals 1/2, right? I mean, okay, we could, but look, remember, right? The original polynomial has all integer coefficients. So I really want to factor this in terms of integers, not fractions. So remember what this is saying, this P of 1/2 equals 0. This is saying x equals 1/2, which is the same as 2x minus 1 equals 0. So this is going to be my factor, 2x minus 1. I'll do the same thing with 2/3. This is saying x equals 2/3 would be a solution of the polynomial equation if this had been equal to 0, which is the same as saying 3x minus 2 equals 0. So that 3x minus 2 is my third factor. So now I'm done, right? Third degree polynomial. I got 3 factors. And by the way, notice here, we did end up with 3 positive roots, just like Descartes' rule of signs said we should. So ultimately, my factorization is going to be x minus 1 times 2x minus 1 times 3x minus 2. Remember, this is easy enough to check. You can always multiply that thing out, and if you do, you will end up back with the polynomial we started with. So let's take a look at this one, right? It's a little different. Instead of being asked to factor, we're being asked to solve the equation. But remember, when we're talking about polynomials, factoring and roots or solutions to the equation are really tightly bound up with each other. That's really what the factor theorem and the remainder theorem are telling us. So I'm going to apply all of my same tools here. First, I see that I have 2 sign changes. All right, so Descartes' rule is telling me that one possibility is I have 2 positive roots. And remember, the complex ones come in pairs. So I could have 0, in which case I would have to have 2 negative ones, right? 4th degree polynomial. There's going to be 4 altogether. Or I could have 2 positive, 2 complex, and 0 negative. Okay. Well, we're not done with the positive ones, right? If there can be 0, if there can be 2 positive, there could also possibly be 0. What possibilities do we have here? Well, I could have 0 complex roots, in which case all 4 would have to be negative. I could have 2 complex roots, in which case there's going to have to be 2 negative. Or all 4 roots could be complex, in which case I would have 0 negative. All right, so let's apply the negative version of Descartes' rule and see if we can't narrow that list down a little. I'm just putting negative x in here for every x. And have you noticed what this does? Right, this reverses the sign of every term that had an odd degree. So this x to the 4th stays positive. The x to the 3rd switches and becomes negative. The x squared stays the same. The x switches. And the constant term, which technically is an even, if you think of it as having a 0 exponent, stays the same. Right, so now I see here that I have 1, 2 sign changes. All right, so what that's telling me is I have either 2 negative roots or 0. So that's going to eliminate this option. I know that all 4 roots are not going to be negative. I'm going to have some, either all 4 are going to be complex, or I'm going to have some mix of positive and negative. All right, so let's see what the rational root theorem tells us. Well, the factors of the constant term are plus or minus 1, plus or minus 2, and plus or minus 4. And the factors of the leading coefficient are just plus or minus 1. That's nice because that's the denominator. Right, so my possible roots are plus or minus 1 over 1, which is 1, plus or minus 2 over 1, which is 2, and plus or minus 4 over 1, which is 4. So if you test these, substituting them into the original here, you should see that P of 2 is equal to 0 and P of negative 2 is equal to 0. Well, it's maybe a little concerning, right? Because I got a mix. I got a positive and a negative, and 1 positive, 1 negative, and 2 complex is not on my list. Right, but that's okay. Let's move forward with this, right, and see what happens. If 2 is a root, then x minus 2 is a factor, and if minus 2 is a root, then x plus 2 is a factor. So we're making progress towards factoring here, right? This is going to be x minus 2 times x plus 2 times something that we still have to figure out. Okay, well, x plus 2 times x minus 2, this is x squared minus 4. So what I'm going to do is I'm going to take x squared minus 4, divide it into the original polynomial there, and what's left is going to go in that squiggly line. Now, if you prefer synthetic division, you are welcome to do synthetic division here. You'll have to do it twice. You have to do it once for the 2 and once for the negative 2 because, and this is why I'm not a fan, synthetic division only works when you're dividing a linear polynomial, first degree polynomial, into the larger one. It doesn't work if you want to divide something bigger, like, say, x squared minus 4. All right, so by doing x squared minus 4 instead, I'm going to accomplish this in one pass, and I just don't think it's that much harder. So I'm going to do x squared minus 4 into x to the 4th plus x cubed minus 5x squared minus 4x plus 4. And this better come out even, right? Because I know x squared minus 4 is a factor. So I'm going to do x squared here. You multiply, I get x to the 4th minus 4x squared. Then we're going to subtract this, so everybody's signs change. The x to the 4ths cancel. Bring down the x cubed. Minus 5 plus 4 is minus x squared. And bring down the minus 4x. So then I'll do plus x. I get x cubed minus 4x. We're going to subtract, so everybody's sign changes, and that's nice, right? Both those parts canceled. And then left with minus x squared plus 4. So we'll do minus x here. We get minus x squared. Excuse me, not minus x. We'll do minus 1. Minus x squared plus 4. We're going to subtract, right? So everybody's sign changes. And that comes out to 0. Excellent. That's what we needed to happen. Right? So that tells me that my remaining factor here is x squared plus x minus 1. Awesome. So now I can finish. Sorry, I'm going to pause if you need to, right? If you're not done writing, but I need the space over here. So now what do we do? Well, we set the factors equal to 0. If you set x squared minus 4 equal to 0, you get x equals plus or minus 2, and we knew that already, right? We'd already found those two, which is good. Okay, so they're still there. They need to be on our list. Then I've got x squared plus x minus 1 equals 0, and you can give it a try if you like, but that does not factor, right? Doesn't factor. So we're going to have to use a quadratic formula. I get x equals negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 1 over 2 times 1. So what's happening to that square root? That ends up 1 plus 4. So this is negative 1 plus or minus the square root of 5 over 2. And there are my answers. X equals plus or minus 2, and negative 1 plus or minus the square root of 5 over 2. Okay, good. 4-3 polynomial, 4 solutions. I'm feeling good about that. But Descartes is still looking over our shoulder, right? Did this work for Descartes' rule of signs? Well, look, negative 1 minus the square root of 5 over 2 is approximately negative 1.618. Sorry, negative 1.618. And negative 1 plus the square root of 5 over 2 is positive 0.618. So, yes, Descartes' rule of signs worked perfectly. I got two negative solutions, negative 2, negative 1.618, and positive 2, and positive 0.618. So this is why I picked this one for us to look at. Descartes' rule of signs does not specify that it's only talking about rational roots. Descartes' rule of signs is telling us about the real roots. All right, so what we came up with, which one ended up being the one that worked, right? It was this one here, right? 2 positive and 2 negative. There are 2 positive roots, one rational and one irrational, and there are 2 negative roots, one rational and one irrational. Absolutely what Descartes' rule of signs told us to expect. All right, so that's 2 good examples, and I know the instructional design theory says the videos should be in the neighborhood of 10 to 12 or 13 minutes, and I'm probably coming right up against that now. So I'm actually going to stop here, but I do have a couple more examples that I want to look at. So in the next lecture, we're going to look at a couple more of these, and then we'll move on to a new topic.